Hello everyone, my name is Rogério, a researcher from P.M.G.P, Portugal, and at the moment I'm a PhD candidate. Today I'm going to give you a presentation on a study of a door when a coach is subjected to a frontal impact. This is a numerical model presentation, and it will take experimental data from a previous pseudodynamic test that was already presented in another presentation. This is presented in the Fourth International Conference on Structural Integrity. The research team includes me, Professor Marco Parente, Dr. Pedro Moreira from INEGI, and the team also includes Engineer Rafael Cunha, Engineer Ricardo Maia, and Engineer Rui Rodrigues from Caetanobus. In this presentation, I will introduce you the project. Then I will present the procedure of the model definition, either the CAD model and the numerical models. Then I will discuss the results and taking advantage of known experimental data, a comparison and validation data is possible. In this work, buckling was the main challenge, so a short talk about this theme will be made. And I will finalize the presentation with some conclusions. Nowadays, testing automotive structures is a crucial moment of new systems in order to pre-validate a structure. There are few regulations to validate heavy vehicles subjected to front impact, and in this work we will evaluate a coach and its safety. In order to proceed, an adoption of R29 regulation is followed, despite of R29 is a regulation indicated to trucks. This study will start with the dorsal system, where the experimental part is a pseudodynamic process that is present in another presentation in the same congress. In this presentation, a numerical part is developed, then a comparison will be made. The R29 regulations say that a pendulum no more than 1,500 kg must impact the front of the vehicle at 55 kJ of energy. Although it was assumed in the experimental part only 3% of the mass would be absorbed by the door, the mass of the pendulum. The numerical models include results from Abacus and Palm Crash software. Then, one of them is chosen to carry on the study. A node displacement from the experimental part is applied as a boundary condition. This test represents an investment to study the structure and how to deal with welded and bonded connections, since in the physics part there were welded connections and adhesive connections that connect the main panel to the frame, the main frame. This work is a component part of the frontal impact section of the shown coach. Represented in B is developed a mock-up to perform R29 test, and the place of the door is in the lateral side as you can see in C. Experimentally, a pseudodynamic test was developed to test the dynamic behavior of the absorbed energy impact. With the results of this pseudodynamic test, an hybrid approach is developed. With a known displacement obtained experimentally, the same displacement is applied on finite element method models. In this slide, you are able to see the door is manufactured with three different materials. The first material is presented in the components, is an alloy steel. The second material, the alloy steel S355, these materials is present in the outside frame, the profiles, and the last material is an aluminium, and this material is present in the front main panel. Regarding the numerical model, there was an opportunity to introduce palm crash in the project, so it would be interesting to have results from both softwares. Then a comparison between both softwares will be made. The FEM model started with Abacus, where the mid-surface and the center line was assigned. This process was made in order to use shell elements and beam elements. These structures have two types of connections, the adhesive connection between the structure and the front panel, and the welded connection between the other whole parts. This is almost a rigid structure. Since there was no rupture and welding cracks in the experimental test, this was modeled as tight constraint. constraining every degree of freedom. Regarding the boundary condition, there was effort to be the most similar as possible to the experimental test. In addition, you can consult in the table in, shown in this slide the element type and the nodes, the number of nodes that was used in this simulation. Regarding Crash software, since we had already the structure meshed, this mesh was imported into Crash from Havoc's in order to take advantage of the work that was already done. The boundary conditions that was applied was similar as Havoc's regarding the integration rule. In the case of shell elements, Belichek's uniform reduced integration was adopted, and Timoshenko theory was adopted to beam elements. Explicit formulation at low velocity is adopted, and hourglass prevention is activated. Let's move on to the first results. In this slide, there is a comparison between both software where the von Mises stress is shown. The contour field is quite similar as you can see, although the maximum stress obtained via Havoc's is higher, 62 megapascal than Crash. The final geometry is quite closer, even the side where the buckling happens, in the mid-zone. A deeper comparison will be made in the next slide in order to choose one software to proceed the study. Like I mentioned before, we have the opportunity to compare experimental data and numerical data. In this plot, you have three different curves, force per displacement. The plastic behavior is quite close in both softwares, although the bigger difference is on the elastic part, that verifies a bigger deviation. Narrowing to FEM software, the software Crash is less stiffer, which permits closer results to the experimental curve. Besides that, Crash simulation is faster than Abacus. In fact, the simplification of the connections using ties could lead to a stiffer structure than the real structure. Another point in the numerical simulation is the buckling effect that induces higher instability, which can result in a challenge to overcome such problem. In order to proceed this work, due to the advantage of Crash, this software is chosen to carry on the study. So, in this slide is present a direct comparison between the final geometry in the experimental test and the numerical simulation, either the front view and the back view. It is possible to notice that there is an excellent convergence of the final geometry. There is a good similarity between both results as we can see. Regarding the strain gauge results, there were placed 6 unidirectional strain gauges. 4 of them are placed in S355 alloy steels, to be more specific, N1, N4, N5 and N6. The other 2 are placed in DC01. These can be consulted with more detail in the other presentation. At the first sight, there is a low variation between the results. Note, the curves fulfilled are the experimental, and the curves represented with points are the numerical. Strain gauge placed near the loading area represents the ones which varies more. But if you look at the orange curve in the plot at your right, you can see there is a reasonable agreement between the experimental curve and the numerical curve. Please note all the strain gauges placed in this material did not suffer permanent deformation. Let's see the other 2 strain gauges placed in the other material. Again, N3 is placed quite near the loading area, so it tends to deviate more. The contrary behavior happens in 2, where there is a good relationship between the numerical curve and the experimental curve. In the experimental test was used the DIC 3D to acquire a full field data of displacement. Here we can compare both results, again remember using Crash. Please note the representation is to x, y and z, considering that x the horizontal plane, y the vertical plane and z the perpendicular plane. In Y and Z, the agreement is reasonable good. In Z, the result in the experimental test come out around 96 millimeters, while in the numerical test come out around 113 millimeters. On the other hand, in Y, the range in the experimental test starts in minus 26 millimeters and goes to minus 1.6 millimeters. In the numerical part, the range starts in minus 36 millimeters and finishes 1.84 millimeters, so the deviation is quite low. The last topic to be mentioned is the regard of buckling, how to overcome this problem. That was the main challenge in the numerical model. The solution to overcome this problem is the including of imperfection in perfect match. Depending the imperfection rate, different buckling behaviors happen. So in order to achieve the best approximated result of the experimental curve, a trial and error should be made. Testing different imperfection rate, different curves is obtained. As you can see, the green curve in the plot, the green curve is the most near of the experimental curve, but the geometry tends to be totally different. There is a need to adopt a median term. In order to conclude this presentation, this work represents a preliminary test and an investment of automotive parts testing. A comparison with experimental data was possible, demonstrating being a good agreement. Regarding the numerical simulation software, both provided good results, although some crash returned results with more accuracy. Strain gauge instrumentation and DIC was implemented, allowing the possibility to have a direct comparison between the numerical model and the experimental model. To sum up, buckling was the main challenge of this structure. This behavior could induce severe and unexpected behaviors. Using numerical techniques and a trial and error to trigger buckling, the closer the experimental test must be used. I would like to acknowledge Crash Project from Inegi and thank you very much for your attention and thank you all the team. If you have questions or doubts, feel free to ask me or to contact me. Thank you very much.